Hello, I'm Mehmet Ansoy for Denver Astronomical Society. I'm the InReach coordinator. We are delighted to have Ben Burke as the speaker this evening. Dr. Burke is the Chief Technology Officer of Transitional Energy of Geothermal Operating Company and Service Provider. He is trained as a geochemist and geologist and has worked in the environmental consulting, oil and gas, and geothermal industries for a total of 22 years. He is also an affiliate professor at the Colorado School of Mines and collaborating professor at Iowa State University. He was one of the junior members of the National Capital Astronomers in 1980s in his hometown of Washington, D.C. He owns a small 127 millimeter Bird Jones telescope. Please, Ben, please proceed with your presentation.
Thank you, Dr. Ansoy. Hope everyone can hear me this evening. I'm delighted to be here to talk about spectroscopy, amateur spectroscopy at that. And really, this is about using light to determine star and planet composition. So I've aimed this talk at a generalist audience, so I'm not expecting any PhDs in theoretical wave physics. If there are any, great, you'll know more than I do. So moving to our next slide. So the outline of what I'll talk about today is, after this brief introduction, I'll talk about answering the basic questions of what is spectroscopy and get into the idea that of light that's both emitted and absorbed. That'll feed right into a brief history of spectroscopy from the kind of ancient Romans onwards. And then we'll jump into what some examples of planetary and solar spectra and stellar spectra look like. And then we'll jump into some observational data that I've collected as a beginner spectroscopist, looking at Vega, specifically Alpha Lyrae, and then conclude with some concluding thoughts. So that's, as Dr. Ansoy said, this is my background. I've been an astronomy nerd since age 8 with the National Capital Astronomers in DC, where I was one of the very few junior members. And so I'm excited that my kids are junior members of the DAS here. So what is spectroscopy? So there are two different definitions to this, and we won't get into the hardcore aspects of the definitions, but in astronomy, we can generally say that spectroscopy is the technique of splitting light into its constituent wavelengths, versus in chemistry and physics, where spectroscopy is the study of matter and atoms using electromagnetic radiation. So they're obviously related, but in astronomy, we're obviously looking at what's outside the atmosphere, whereas in chemistry and physics, it's almost more of an inward look. So no talk in spectroscopy is complete without a electromagnetic spectrum chart. So this is the example of wavelengths from gamma ray and X-rays through the visible light with ultraviolet and infrared on either side of it. You can see how narrow a band of the electromagnetic spectrum visible light is. That moves into microwaves and ultimately into radio waves and super long wavelength items here. So we'll be dealing with breaking apart visible light into its constituent components. Spectroscopy also happens at the infrared wavelength, in X-ray wavelength as well. And as a geochemist, something I've worked with quite a bit is X-ray fluorescence spectroscopy in determining what different mineral constituents are, and particularly in solids. But we won't go there today. We'll stick to visible light. So some examples of kind of the useful aspects of the electromagnetic spectrum. Nuclear power essentially comes from gamma radiation. We have medical X-rays, which we're all familiar with. Sunburn happens just on the ultraviolet side of the visible light spectrum. Remotes work in the infrared territory. which is also essentially the thermal territory. So human body radiates heat. That's another, that's that thermal example. Microwave ovens, cell phones, FM radio, and then AM radio head off into the microwaves and the different types of radio waves. So the spectrum broadly is something that's been quite useful to humanity over the years, outside of what we can just literally see. So we can jump further into the definitions. So this is the definition. This slide is an example of emitted light versus absorbed light and reflected light. So the pixels that you see on the left side of your screen in that green square are being emitted by the LEDs in your screen towards you. That's an active process. And then taking the picture on the right-hand side of the train station in Glenwood Springs, what we're seeing in the image here is that sunlight is absorbing every color except those which are seen here, which are reflected to the camera. So this is an example broadly of emitted light on the left and absorbed and reflected light on the right-hand side. So some Earth-based useful aspects of spectroscopy are wrapped up in Landsat series of missions. Satellites, the Landsat 1 was launched in July 1972, and these are US government satellites, US Geological Survey specifically. We're now into Landsat 7, 8, and 9 are concurrent missions that are up there. And these are multispectral data. So these are data that work not only in visible light wavelengths, but also in ultraviolet and infrared. And so they can give us images like this one of part of Nova Scotia here. And so this image is a good example of thermal absorption and reflection. And what we're seeing here is a blue land surface, Nova Scotia, as I mentioned, and warmer ocean waters surrounding it. This is from the wintertime, hence the land is colder than the ocean. And the color scale there on the right-hand side is color in degrees Celsius. So that's the example of kind of one application of spectroscopy and how that works. We're splitting light, splitting that electromagnetic spectrum up into its components and then visualizing them. So there's this is a field that is, as I mentioned, certainly more broadly applicable than what we'll talk about in astronomy today. And of course, not all light makes it out of the atmosphere. Our atmosphere absorbs certain amounts of it. So on the bottom hand, on the x-axis of this plot here, we've got wavelength from on the left-hand side, 400 to 900. So that's the blue, green, and red part of the visible spectra heading off into the infrared and additional wavelengths. And those colored boxes there with the numbers inside them are the different bands that Landsat uses. And so the y-axis is atmospheric transmission from 0 up to 100%. And so most light, well above infrared even, transmits through the atmosphere. And when we're down in the visible spectrum, not all light transmits through it. So this is something we take into account when we're doing astronomic spectroscopy, because we're not only dealing with whatever our source of light is, whether it's a star or a planet, but we're also conscious of how our own atmosphere here on Earth, what it takes essentially from that light as it gets to our eyes and to our cameras. So here's an example moving into the astronomic realm of an emission spectra. So when a gas is heated very hot, different element, those different gases as elements have unique emissions, and these are emitted as lines within a spectrometer. So with hydrogen, for instance, of course, a big constituent in stars and certain planets, we can see these different, just a handful of lines. Helium, another very light element, has again a different set of lines. Carbon, different again. So different elements are very useful, and whether they're gases or solids that are being burned, have their own unique signatures, and that's part of the fun, really, of doing spectroscopy on different stars or different items, to take the overall emission spectra here and break it up into its constituent components. So when we put all these together, we've got different kinds of spectra. We've got continuous spectra, and there's an example there. That's the kind of rainbow color bar that we're all familiar with seeing in astronomy and in various places. We've got the emission examples, the bright lines we saw in the previous slide, which can be a system, which can be indicative of specific minerals, elements, or combinations of minerals and elements. And then you've got kind of what reality is, which is a continuous spectra with absorption or dark lines, sometimes with emissions in that. And the absorption, again, can be from our own atmosphere, and it can be from the atmospheres of planets in particular. So there's really two ways of breaking light up into its constituent components in astronomy. There's prisms, which are the kind of the older standby, and then there's grates or diffraction gratings. And there's an example of the prism on the left and gratings on the right, where light comes in from a given light source, in this case a star, and then based on its wavelength is broken up because different wavelengths diffract at slightly different angles. So moving into the history of astronomic spectroscopy, it was the ancient Romans that first identified you could take a prism and break up light into its constituent parts, except the ancient Romans didn't quite grasp kind of what that was. It was a pretty color, essentially. And it really was in about the 1600s, in the 17th century, that several scientists, Newton kind of gets a lot of the credit for doing 16th century work on this, but there are a number of other scientists that worked on understanding the nature of light. However, because of kind of poor optics, there wasn't all that much advancement in the science. It really wasn't until the 19th century that some German scientists, particularly Joseph Fraunhofer, discovered solar absorption lines, which are now known as Fraunhofer lines. And he was also the first one to quantify the wavelength scale, so to understand that, to put in a consistent manner so that different spectra gathered from different different research institutions, different observatories could be standardized and compared. And it was around the same time that scientists realized that different elements, like salts in particular, when burned, emit different spectra. And so that began the idea that spectra relate to the chemistry of what's emitting that light, or in some cases reflecting that light. So bringing the idea of spectroscopy out of the lab, out of burning salts and simply breaking apart sun's light to the stars, credit really goes to a husband and wife team of William and Margaret Hudgens, who are English, not to be confused with Huygens, who was a Dutch scientist who worked 200 years beforehand. They did some groundbreaking work in the 1860s, and they were the first ones to figure out that stars are composed of the same elements as those present here on Earth. And they were able to determine the axial speed of Sirius by the redshift in its spectra in 1868. They were the first to collect a spectrum of a planetary nebula in 1864. And other workers following them into the late 19th century discovered X-rays, and the idea of doing spectroscopy outside of the visible light spectrum was born. And that further was able to quantify the chemistry of what was emitting that light. So again, with planetary versus stellar spectroscopy, this is a good example here that I put together of emissions versus absorption. So we've got our sun on the right-hand side. It's emitting light to Earth, which is reflecting back to our eyes if we were just out hovering in space as truly omniscient observers. That light is also hitting other planets, such as Neptune, shown here as a squishy character. And then those other planets are absorbing that radiation and only emitting some of it back to us, or rather reflecting, some of that back to us. In the case of Neptune, reflecting a lot of blue light back to us. And then that's being further changed by oxygen and water vapor in our own atmospheres. So we have to, when we see a spectra, we have to constantly think about, is this an emission spectra or is this an absorption spectra when we're looking at astronomic spectra. So I'm thinking of the planets. I've got Venus here on the left with a 96% carbon dioxide atmosphere. We've got Mars with a 95% CO2 atmosphere. Of course, atmospheric composition isn't everything. With Mars, we can actually see to the ground in many cases, although there are clouds and storm systems that move around that planet. When we move out to the gas giants with Saturn and Jupiter and Saturn, we're dealing with giant balls of hydrogen, with helium being the next big constituent. And kind of the same goes out for, this is an example of Neptune. Uranus is quite similar. But there the percentage of hydrogen is actually a little bit lower, and we have more helium. And both on Neptune and Uranus, we have about 1% of methane, which is that CH4 component there. Now, one fun thing about Mars, of course, is that while we can look at the spectra of Mars, and again, knowing that Mars is not a star and is reflecting light back to us. Of course, as a lot of US and European missions have been in orbit around Mars, they're doing the same thing the Landsat satellites are doing on Earth, just on Mars, with very close-up spectroscopy. And of course, there's spectroscopy going on the surface with the various instruments on both the Curiosity and Perseverance rovers. And that's able to get into the Mars chemistry. It wouldn't quite be the geochemistry, the chemistry of the rocks and material that those rovers are encompassing. So Mars is a fun study, so to speak, in a planetary spectroscopy and zooming in scale-wise to very specific minerals on the surface. So an example of a planetary reflectance spectrum, and this is a Mars spectrum. This is not one collected by me, but by a guy in France named Christophe Pellier, who's published a book on how to image and do spectrographic work on the planets. And it's really quite a good read. And I'm glad to share this slide, or the whole deck, or any of the links within it. But what this very colorful diagram shows here is we've got the Mars spectrum in red. Let me turn on my, go back one. I'll turn my laser pointer here. So here with the blue line is the spectrum of Mars. And then here is the solar spectrum. And they're very similar. They show similar absorption bands, and you can see this. Mr. Pellier has in orange mentioned where calcium and hydrogen beta lines and different solar spectrum items that are both present in the solar spectra and the Martian spectra, really indicating that what we're dealing with is reflected light to a great extent. But there's also some absorption going on. Mars is, after all, the red planet. And so the highest relative intensity here is in the orange and red areas, with some of the blue and green having a lower relative intensity, meaning they're getting absorbed by both the planet and our atmosphere. And same thing up in the infrared band as well. That's getting absorbed. So if we were to look at, let's say, Venus, it would be a lot flatter. And so it wouldn't be red specifically. It would be essentially all the colors mixed together, which is mostly white, Venus is more of a sort of creamy yellow color, but it's a much more even reflectance of solar light. So we can compare that one to Uranus, and this is also from Mr. Pellier, again, with solar being the one in orange, the actual planetary one, very clearly showing these big dips, which he's labeled as CH4. So these are, even though the atmosphere is only 1% methane, what this spectra is indicating is that there is methane in the atmosphere that's absorbing that sunlight before it's reflected back. And then here on Earth, the oxygen and the water vapor in our atmosphere show up as small spikes or dips here. And that's, we can go back to this last one. And with Earth is in green here, we can see these big dips for oxygen, water vapor, and another one for oxygen. So we're always looking out for that not only the solar effect, but also the Earth atmosphere effect. So this, to move from planets to stars now, this is an example on the left-hand side of star spectral types. And so these are all the types of stars that are out there. O, B, A, F, G, K, M. And some of these at the top have very few lines in them, and towards the bottom they have many lines in them. That would be probably the best way to characterize this. And fairly long ago, it was noticed that star type correlates, and the color of the star correlates to approximate surface temperature. So these O and B and A type stars, the ones at the top here with very few lines, are very hot stars, over 25,000 degrees Kelvin for the type O stars. By the time you get down to the K and the M, we're dealing with very warm colored stars. So think of Sirius and Scorpio. These are stars that have Kelvin temperatures that are similar to light bulbs. A lot of warm light bulbs you can go buy at the hardware store have Kelvin temperatures of, let's say, 2,800 to 3,000 degrees Kelvin. Whereas the kind of daylight bulbs are the ones that are about 5,000 Kelvin. And so that color is apparent to our eyes from stars, as well as being apparent from for light bulbs. So if this is one way here of characterizing star types, this type of diagram, or just commonly known as the HR diagram, is both a conceptual and an observational way. And this is of categorizing stars, and this is really a cross plot here. We've got luminosity on the y-axis, and we've got, again, that Kelvin temperature on the x-axis. And so when you plot those up, you get those O and B type stars up here, and they grade down to the K and the M type stars with much lower temperatures down here. And then we've got a few things that don't fit this almost linear plot. You've got supergiants like Betelgeuse and Antares, Deneb and Rigel, some of the giant stars as well, and then some white dwarfs that sit out in this region. So if this is the conceptual diagram on the left, this is the observational diagram, kind of showing what this looks like. And this is a plot from Wikimedia Commons here. So now we can switch into observational mode. It's time for some fun, not just for cats observing the Cat Eye Nebula. And this is not my own cat. This is an image taken from Reddit.com's cat channel. This is the proverbial slide in the middle of the talk that checks to make sure people are still awake with some humor. So I jumped into making my own spectral observations here. So on the necessary items I needed for this was a telescope, and of course anyone can spend from $75 up to infinite sums of money for a telescope. There's mine on the right-hand side. It's about the cheapest scope you can buy. It was rated by a telescope rating site as one of the worst telescopes you could possibly buy. So nowhere to go but up, and I've made a purchase in that regard recently. But it does get the job done, certainly when it comes to planetary and moon imaging. You need a spectral grating. In this case, I went with the Star Analyzer 100 from Field Tested Systems at RSpec astro.com. You need a camera with which to capture these spectra. And so I have the basic entry-level Orion Starshoot 3 megapixel camera. Again, you can do this with DSLRs. You can do this on film. You can do this any way that you would typically do imaging, solar astro imaging. And then you need some spectral interpretation software. And RSpec has spectral interpretation software. There's a 30-day free trial on that. And then it's about $100 for $109 for a perpetual license. So when you first set everything up and you get out there on a nice a day or a nice evening with whether it's great viewing and you're at the top of Guanella Pass, or whether it's a little bit of moisture in the atmosphere. This is a fairly forgiving type of science, but this is the view you will see through your viewfinder or through your camera when you have spectral grading. You'll see this is this point of light, or this squiggle. Here is Vega on the 23rd of November, and then there's the spectra coming off it. And so this is what is imaged in the camera and then goes into the software. So it's no more difficult than this. And I should mention, this is an untracked image. The little tiny telescope I have does not have tracking. And for brighter objects and planets, certainly that is not a problem at all. So when you bring the image into the software, you rotate it so that you can image or have inside this line here both the star itself and the spectra. And the software automatically builds this diagram here of relative intensity on the y-axis and the number of pixels. So this is basically a histogram that shows that here we've got this dot of light. Move to the next slide. This dot of light here is Vega, and that's a white pinprick of light there. Hence the stack, the very narrow stacking. And then we've got our blue, green, and red spectra here, and that's what's noted here in this pixel bin. And of course, the fact that this is in pixels is just the first step. So once we've got this image in here, the next aspect is to calibrate the image. And that's what turns the x-axis pixels into either nanometers or into angstroms, which is then where kind of where spectroscopy really gets fun. So we go to the next slide. I've brought up the calibration wizard here. Again, the same image on your left, and we call this the 0 point. And so I've entered that information right here and check the little box for 0. And then with Vega, Vega is a type of star that has a very, very apparent hydrogen Balmer line, meaning there's a hydrogen, this dip in the spectra here is indicative of hydrogen. So we know that is the hydrogen beta line, as it's called, that happens to be known at, or happens to occur at a wavelength of 4,861 angstroms. And so knowing that the distance from there to there in pixels is 4,861 angstroms, voila, we have our calibration. So now we have our x-axis it's the same data, it's now transformed into angstroms instead of pixels. And then we can go through and look for other type of data. So this is the same view here, just with this camera, the software from RSpec, putting this hydrogen Balmer line in. And then we can take the same one and put in all the other hydrogen lines, because the Balmer series has several of them. So we've got hydrogen alpha, beta, gamma, delta, ellipson, and zeta. So these are also, we all know the Greek alphabet from COVID naming conventions, but luckily it's been used in astronomy long before that. So this is probably the most obvious example here of kind of how to do this and what absorption, what emission spectra look like. And this hydrogen one's a great one. So we'll end with that in terms of the observational data. And there were some best practices I picked up along the way in talking to folks. And one of those is to use a focal reducer on planets to really get a point of light as best as possible. A star, of course, is always going to be a point of light. But for instance, even with a small, simple telescope like mine, you can still bring up the disks of Venus and Saturn and Jupiter. But when you do that, even with a very sharp focus, that tends to take the spectra and kind of blur it a bit, and that makes the analysis of that spectra a little more difficult. So using a focal reducer, if needed, on your planets to get to a point of light is good. Sharp focus is important. You might think, well, light's light. Why does focus matter? But it really does, because that clean spectra from the grating is dependent on having that point of light be very sharply focused. Something I didn't do at all in what I showed you is correct for instrument response. So the camera and the optics, the telescope change. There's a little bit of instrument bias in there in terms of into that spectra. So there's a way through the software to go in and correct for the CCD camera you have and correct for your optics. And that correction happens at once. You're not correcting for both. But correcting for instrument response is a way to get sort of the clean spectra that you see when you Google different spectras online. Again, starting with Vega is always a great place to start because the Balmer lines are so easy and they're all right there. And then as you get more into it, always keep in the back of your mind that idea between emission spectra, reflection spectra, and what's absorbed. And stars versus planets are where that's most important. So I've got some links here. The link from Christophe Pellier, which is planetary astronomy and imaging.com with dashes in between the words there. Lots of great content on planetary spectra. And then RSpec-astro.com is a huge resource for beginning spectroscopists, both on the methodology side, but also kind of examples of what you can see with that. So some concluding thoughts. So amateur spectroscopy is a really rewarding way to take your observing from just looking at pretty views to really quantifying the universe around you and doing some citizen science or some professional science. It can be done with low magnification and no tracking in a simplistic sense. There's no special computing power needed. Your average modern home computer will run, generally Windows computer will run this necessary software. So with that, have fun and happy observing, and I'm glad to answer questions. So thank you for listening.
Thank you, Ben. You can maybe stop the sharing so that we can see everybody.
Sure.
Okay, thank you. So I'm going to pose my first question here, Ben, and that would get the other people ready for their questions. And my question is actually related to our own planet. How do we use spectroscopy for studying climate change?
Studying climate change. So that using spectroscopy for Earth-based observations or satellite observations of Earth, the most effective way in doing that would be to look at time series measurements. So measurements collected over different seasons and over different years, looking at probably water vapor and particularly the thermal side of things. So using thermal emission spectra would be the best way to do that. But it would be quantifying change over time and determining if that change is human-based or is natural based on, say, seasonality.
Can we tell the difference with spectroscopy as to whether it is human-based?
I mean, the biggest kind of quantitative example of effects on the planet are the Mauna Kea measurements of CO2 that were known to about 350 parts per million CO2 kind of in pre-industrial times, and is now about 410 parts per million. So that specific level would not be discernible from satellite methods. It would be the effects of climate on weather that would be the most effective ones.
Okay, thank you. Those of you who would like to pose a question, please raise your hand. I hope I can see everybody. I see Dina, you are raising your hand. Dina, unmute and.
I had one question I put further up. So in junior high school, we did some experiments with spectra, burning certain elements to correlate those spectra, with the elements. Is that what we would see in a star versus what we would see in the atmosphere of a planetary atmosphere?
Yeah. So the kind of the burning of different elements, or the fluorescing of different elements, is highly analogous to what you'd see being emitted from a star, versus say with Neptune and its or some of the methane lines. Those are absorption. So not something that would be discernible kind of from a high school chemistry physics level. Yeah.
Okay, okay. And my other question was, is there a version of the software for a Mac?
I know for RSpec there is not, and that definitely pains me as a Mac guy. But there are other providers of gradings and software out there
Okay.
that I'm not as familiar with. But you could always run boot camp, I guess, on the Mac to have the Windows software work within the Mac world.
Oh boy. I'll talk to you about that if I get that far. Thank you.
That is a bit challenging. There is a question from Tim Hibbs. Tim, do you want to pose your question, or shall I read it?
No, that's fine. I'm happy to pose it. First of all, thank you very much for the presentation, Dr. Burke. It's educational and fun. The question that I've had for a long time is, you mentioned that the husband and wife team first identified the redshift of a star's rotation. I can't remember which star you were talking about. And that brought to mind the question, how do we determine what is shifted from what a redshift is? What defines zero? And then what scale is applied to a shift to determine the speed, either toward or away from the observer?
That's a great question, and certainly we're used to thinking of spectra in terms of thinking about Big Bang and stars moving away from us, and so redshift being defined there. That is outside my area of knowledge in terms of understanding how the axial speed turns into redshift. That's something I'd have to get back to you on.
Oh, you needn't necessarily get back to me. I mean,
there are probably books on that too. So,
yeah. Okay. Well, thank you.
Okay. Any other questions from the audience? I see John Bickle. Unmute and ask your question, please.
Yeah. First of all, Ben, I also have been using the RSpec software, and for low resolution stuff, it's pretty good. I've had it for about a year. I'd recommend people playing with it. It's one of the things I did as a project was I started looking at the Orion galaxy, all the major stars in there, and then I came up against Betelgeuse. And one of the things you find is that Tom Field, the guy that is the developer of RSpec and all that. I had quite a dialogue with him because we couldn't easily use the hydrogen beta point to calibrate the spectra we got. So we iterated, and he just seems to be a wealth of knowledge that he's willing to share and spend time. And I think we emailed back and forth about 6 times before we figured out how to do it. And he's got ideas to do stuff beyond what's in the software, which is handy. But I really recommend the product highly. Very usable, user friendly. It is low resolution. If you were trying to get the speed of recession of a galaxy, you'd need a lot more precision to see the Doppler shift, like in the hydrogen alpha lines or something like that. You can't see it with RSpec.
Yeah.
Other than that, it's a good tool.
And I interacted with Tom as well in preparing for this, and agree with you. He's a wealth of knowledge and a really nice guy. So,
and he doesn't mind. He doesn't mind sharing. Yeah, I love it.
Definitely.
The next question is from Jack. Jack, unmute yourself.
Yeah, just a couple of comments. There is an amateur spectroscopy group. I think there's largely in France, and people like Ed Wiley and Dave Cottrell have given talks on this at Okie Tech Star Party, and they're doing with 8-inch telescopes, they're doing the kind of stuff that gets published in peer-reviewed papers. So that's something to think about. I've been caught by surprise. I don't have any of the data, but I'll be happy to post this to our discussion group when I find it. And the other comment on the velocity of Sirius, I think, I'm not sure what you meant by axial velocity. It's radial velocity, which is the speed toward or away from us. And that's done by the red or blue shift. And the calibration on that is the wavelength of the element at in the laboratory. You look at the spectrum in the laboratory, and that is your zero wavelength. Then, with a good spectrograph, you measure the change in wavelength between the lab standard and your star, and that change in wavelength is proportional to velocity over the speed of light. So it's a fairly straightforward calculation. And I have to tell a funny story that VM Slifer at the Lowell Observatory back in about 1912 was measuring radial velocities of galaxies and coming up with some surprising results. There was a documentary not long ago. It took him, I think, about a month to get a good velocity. There was a documentary where these guys were out there on La Palma, which is currently having its issues, with a 10-meter telescope. And the guy said, let's look at this thing. He put a cursor on the galaxy. 10 minutes later, he had a spectrum, ran it through the software, and 15 minutes later had the radial velocity in under a half hour. Took Slifer about 3 months. So yeah, we've come a long way. But at any rate, that's kind of how that's done.
Excellent. Thank you for that.
Okay, thank you, Jack. I have Mike next to ask a question. Mike, unmute yourself, please.
Yeah, thanks a lot. First of all, excellent presentation. Really enjoyed it. My question or comment has to do with what do you do with these observations once you've got them? And I think Jack began with an answer. I'm a member of the AAVSO, and there is a spectroscopy section, and there are lots of amateurs and professionals who are inputting data. And you can use a telescope, you can use a plain camera with this the spectral device on the cover, and get good results that astronomers can use. So it's more than just having fun, but that is for me the beginning. However, you can actually contribute to the science. I don't know that you have to be a member of the AAVSO or some of these other groups, but they are screaming for data. Astronomers need data on some stars that even a DSLR can pick up, or a small telescope. So we're in a very wonderful position where we can actually make contributions. So
absolutely,
you did a great presentation, and try to use these observations to help the whole field. Thanks again.
Thank you, Mike. I actually have Forrest with some comment. Forrest, unmute yourself.
Hi, everybody. Yeah, so I was just making a note. I'm actually working on a project right this through my graduate program. A couple weeks ago, we remoted into the university's observatory in Grand Forks, North Dakota, and used the spectrograph. I've forgotten the model number. I'd have to check my notes, but yeah, we took measurements of Vega and we took measurements of Altair. So I have my Spectra, and I have to calibrate the data now and run it through the software and match up the grids as you saw in Dr. Burke's presentation. But yeah, I'd be more than happy to share anything after I get it calibrated, assuming I do. So
wonderful.
Thank you, Forrest. I do have both Mike and Jack's hands still up. Do you have some new comments, Jack or Mike?
No, I was just going to go on about what Mike said, that they're in the AAVSO, but there is a group that does stellar spectroscopy. I commented on that a minute ago, that is doing peer-reviewed journal articles. they publish their own papers, their own journal. And I will post that on our general discussions page. Since I don't have it off the top of my head, you guys caught me by surprise with this one. And again, I will add to the other comments, excellent presentation.
Yes, yes. Any other comments, questions from anybody?
I have a, oh, I'm sorry, go ahead.
To say there's on cloudy nights, there's a spectral subsection under some of the imaging, and there's some really good data presented there as well, informally. Go ahead, Tim.
I'm thinking about spectra that I have seen. I guess in particular, the ones that I'm recalling are absorption spectra of objects in the sky. And these spectra that I've seen, I guess are raw spectra, are just filled with absorption lines, just hundreds of them. And what comes to mind, you were very clear in your identification of the hydrogen beta line when looking at Vega. But just with hydrogen, the simplest of all elements, there were, what, 7 different spectral lines corresponding to different levels of ionization, I guess. I'm not quite sure what those represent. But how does one tease apart a spectrum that is so complex and to determine not only what elements are being absorbed, but the percentage composition of those elements in the spectrum?
I think for that, that's where the another gentleman made the comment that it took Cypher, a few months to do his spectral work, and it took software half an hour. So in that sense, the software can really help deconvolve this overlay of different elements that all, as you said, present themselves together and present almost a bewildering array. But there is an interpretive component to it in the end, where if the subject matter, if the star, the galaxy is not well known or understood, then it becomes an interpretation. But usually one that builds from other given examples in peer-reviewed literature. So there can be different degrees of certainty, but the software certainly helps deconvolve that versus sitting there with a giant book saying hydrogen has these, and helium has these, and so on, sodium and calcium and carbon.
Well, and you showed methane. That's kind of surprised me a little bit, but that would be in a planet, I suppose, right? Yeah, thank you.
Yeah, you're welcome.
Okay, Jack, again, you have some further comment?
Yeah, I was just on this business of identifying a spectrum. I think it was Tim that was going on about that yes, it is unbelievably complicated. And at the telescope, and I'm talking about 50 years ago, so it's different now, but you have an iron arc or you have a carbon arc, and you do you set off this arc near the spectrograph, and that puts the spectrum of whatever that stuff is, carbon or iron, onto the photographic plate, and then you can correlate between the comparison spectrum, and that goes a long way in identifying stuff. And then, of course, there's the chemical physicists or the physical chemists that go through and calculate all the energy transitions and predict where the spectrum lines are. And in the hydrogen spectrum, there's a lot more than just the lines that the doctor was talking about were the Balmer series, which are in the visible. There's the Passion series, which I think is infrared, and at various energy levels, there's dozens of hydrogen lines as well in different regions of the spectrum. So they can get kind of messy, but it is tractable. So on that note, I think I'll go away.
Okay.
Thank
Well,
you.
Ben, thank you very much. I think this was a very informative, excellent presentation. So we very much appreciate preparation and delivery of this presentation. Thank you again.
It was my pleasure.
Okay. So have a good evening and good holidays to everyone. Bye.